Hi guys, this is lesson 7.2. It's called Division Properties of Exponents. We are going to be dividing our monomials using properties of exponents, and we're going to be simplifying expressions that have negative and zero exponents. First up, let's talk about dividing monomials. We can use the principles for reducing fractions to find quotients. That's the word you use when you're dividing. Of monomials, like 10 squared over 10 to the 1. So look for a pattern. If I had 2 to the 7th over 2 to the 4th, that would be 2 times 2 times 2 times 2 times 2 times 2 times 2 on top of 2 times 2 times 2 times 2. And notice that just the same as we would simplify fractions, we can cross off matching 2's that are on the top and the bottom. So notice that we could say cancel, 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 cancel. And what's left is 2 times 2 times 2 on the top, or 2 to the 3rd. Okay, in the second one, we have t to the 4th and t to the 3rd. And notice that we canceled 3 of them that matched up, and we had this one straggling left over here, and we just have t left over. So how can we find some patterns in that? Okay. To divide two powers with the same base, subtract the exponents. So that means that for all of our non-zero numbers, obviously 0 causes a problem. So we're just looking at numbers that aren't 0. We are going to take our m and p here and subtract them. So a to the m over a to the p is going to be a to the m minus p. Let's go back to the 2 to the 7th and the 2 to the 4th. Was that not 2 to the 7 minus 4 or 2 to the 3rd? When we subtract, we're just dealing with the things that are going to cancel out. T to the 4th over t to the 3rd is t to the 4 minus 3, which gives us t to the 1. And there's our t to the 1. All right, look at the example. G to the 3rd, h to the 5th over gh squared. We are just going to need to cancel the things that line up. And so you could think of it like this. Separate out your g's, separate out your h's. And if I have 3 g's on top of 1 g is going to cancel out. So I can just do the math with subtraction. I can say 3 minus 1. It's the same as dividing g to the 3rd over g by just going g to the 3 minus 1. G to the 3 minus 1 is g squared. And then I'm going to do h to the 5th over h to the 2nd. So just showing you this so that it keeps going in your head. Here's h to the 5th over h to the 2nd. And we would notice that 2 of those would cancel, leaving 3 of them. That's the same as if I do h to the 5 minus 2. Top minus bottom gives me h to the 3rd. And that's what I saw. Pretty cool. All right, so we can use the product of powers property to find the powers of quotients for monomials. So let's look for let's look for a pattern here. So if I have 3 to the 4th, and then I have to the 3rd power, the 3 is on the outside, I know that's going to be 3/4 times 3/4 times 3/4. So notice that I have 3 3's on top and 3 4's on the bottom. So that exponent actually goes onto the number on the top, and it goes onto the number on the bottom. So notice that if I have c over d squared, I'm going to end up with c squared over d squared. Just like we saw before, the exponent on the outside applies to every piece that's on the inside. So here are the words. To find the power of a quotient, find the power of the numerator and the power of the denominator. In simpler words, put the exponent that's on the outside of the parentheses onto the bottom and the top. Okay, so if I have 3 to the 5th to the 4th power on the outside of parentheses, I will end up with 3 to the 4th over 5 to the 4th. Or if I do it with a variable, r over t, all of that to the 5th, I'm going to have r to the 5th over t to the 5th. All right, so let's look at this example. I have to simplify 3p squared over 7 in parentheses squared. So I know that that squared is actually going to apply to every single piece of what's going on inside. There are different ways to write this out to make sense, but you might just want to start going, okay, I know I'm going to have 3 squared. I know I'm going to have p to the 3rd squared. And I'm going to have 7 squared. So depending on when or how you want to do your numbers, 3 squared is 9. P to the 3rd squared, we have to do the 3 times 2 to get p to the 6th, because remember we're doing p to the 3rd twice. So we end up with 6 of them. And then on the bottom is 7 squared is 49. Careful not to do 7 times 2. 7 times 7 is 49, and so that's a much bigger number. All right. All right, so what happens if I have a 0 exponent? It is pretty interesting. So they're going to show you a couple of y answers. If I have, say, 3 to the 5th over 3 to the 5th, then I'm going to end up with 3 to the 5 minus 5 using the rule that we just learned, which is 3 to the 0. Well, 3 to the 0 is not going to be 0 because 3 to the 5th over 3 to the 5th is not going to be 0. If I have all those 3's over all those 3's and I line them all up and cancel them, remember that we don't cancel and leave behind zeros, we leave behind 1's. And all these 1's simplify to just be 1. 3 to the 0 is actually 1. Okay, look at method 2 actually looks pretty much the same because I just wrote that out when I was looking at method 1. So either way, what we have here is the 0 exponent property. And the words are this: any non-zero number raised to the 0 power is equal to 1. So a to the 0 is going to equal 1. Okay, so it doesn't matter whether it's a letter or a number. 15 to the 0 is going to equal 1. B over C to the 0, if it's all to the 0, is going to equal 1. 2 over 7 to the 0 is going to equal 1. Anything to the 0 equals 1. There are more explanations for that. I would love to chat about interest, but we haven't seen that equation just yet, so I will save it. And I just need you to know that anything, look at this big whole problem right here, anything to the 0 power, that whole thing's just going to be 1. And then if we have these funny little pieces like this, x to the 5th, y to the 0 over x to the 3rd, well, just pick those right out. X to the y to the 0 there is just going to be a 1. We don't even need to deal with it. We just need to deal with the x to the 5th over x to the 3rd, which is x to the 5 minus 3, which is x to the 2. That's how many x's are left over after I cancel them. All right, so here, another easy problem. Anything to the 0 power 0, so everything in parentheses to the 0, that's just going to be 1. Here, when I see that d to the 0 for 3a, I'm just going to make it a 1. I don't need to do anything there. The rest of the problem here, b to the 4th over b to the 2, is b to the 4 minus 2, which is 2, and c to the 2 over plain old c, which is c to the 1, is c to the 2 minus 1, which is c to the 1. I don't have to write the 1 on the c. I can just write it like that. Okay, let's talk about negative exponents. So negative exponents are not negative numbers. The negative is just a way of saying, put me in the bottom of a fraction. Or if it's in the bottom of a fraction, it's saying, put me in the top of a fraction. So the negative exponent is an unhappy exponent. It wants to live not where it is. If it's in the top of the fraction, it wants to live in the bottom. And if it's in the bottom of the fraction, it wants to live in the top. As soon as you move it where it wants to be, it becomes positive and happy. All right, so for example, look what happens if I'm doing c to the 2 over c to the 5. I get c to the 2 minus 5, which is c to the negative 3. Well, what the heck does c to the negative 3 mean? Look over here at method 2 and you can see it. In the first place, I had c times c on the top, and I had c times c times c times c times c on the bottom. So these guys canceled and these guys canceled, but I had 3 left on the bottom. It's the same as 1 over c to the 3rd. 1 over c to the third is the same thing as c to the negative 3. Okay, so if I write c to the negative 3, that negative 3 is saying, put me in the bottom of a fraction. And so if I do that, it will move down here. We never leave behind a 0. We always leave behind 1s when we're simplifying fractions. So, pretty crazy. Words. For any non-zero number a and any integer n, if I have a to the negative n, it's the reciprocal of a to the n. So a to the negative n, the reciprocal of that is a to the n. Or if I want to say this, a to the negative n is going to equal 1 over a to the n. Don't let this be too scary or complicated. 2 to the negative 4, it's just the negative 4 saying, put us in the bottom of the fraction. So it goes to live down here in the basement. And you just keep a 1 left behind on top. So that's actually the same as 1/16. If I have 1 over j to the negative 4 here, then this j to the negative 4 is very unhappy. It wants to go live in the top. And if I put j to the 4th on the top, I will have a 1 in the bottom. I don't need to write the 1 in the bottom because that's the same as writing a whole number. So I'm just going to have j to the 4th. So a little bit of another explanation for that. Let's say I have 2 to the 1. That's going to give me 2, right? 2 to the 2 is going to give me 4. 2 to the 3 is going to give me 8, and I could keep getting bigger and bigger, right? We have seen that 2 to the 0 is going to give me a 1, but 2 to the negative 1 is going to actually give me that reciprocal, 1 over 2 to the 1. Okay, 2 to the negative 2 is going to give me a reciprocal, 1 over 2 to the 2, which is 4. 2 to the negative 3 is going to give me 1 over 2 times 2 times 2, which is 8. So notice that when I'm going this way with exponents, we are getting exponentially larger. To 1, to 2, to 4, to 8, to 16, to 32. And notice that it's doubling every time. It grows very quickly after this. But if I go backwards with negative exponents, I just keep going, getting smaller. 1 goes to 1/2. Notice it halved. And 1/2 goes to 1/4. That's a half again. And 1/4 goes to 1/8. That's half again. And so what do you think the next one is going to be? 1/16. And then 1/32. It looks exactly like the exponents going up, only the exponents are going negative, and they're causing us to, instead of double things, they're causing us to half things as we go backwards. And we get smaller and smaller and smaller pieces, but they never go away because, of course, half of something is always something, right? But the pieces get very, very small. All right, let's look at example 4. So I have some unhappy exponents here, and all I have to do is sort them out to make them happy again. Notice that n is fine. N wants to stay there. N is not, oh, wait a second. No, n is not fine. N has a negative 5. Take that right back. N to the negative 5 wants to go live in the bottom of the fraction. So I put him down there with his exponent, and then he's happy. So take away the negative. Okay, p to the 4th is perfectly happy living on the top, so we are going to leave him there. In the bottom of this fraction, I have an unhappy r. R to the negative 2 wants to live in the top instead. So I have r to the 2. Notice I took away the exponent because r to the negative 2 in the bottom is now very happily living in the top. So we take away the negative. And so that's all there is to it. We're just sorting those little guys out. Typically, we put them in alphabetical order if there's any confusion as to where to put these things. All right. Let's move down here. Have a quick look at this order of magnitude. And order of magnitude is a quantity of a quantity is the number rounded to the nearest power of 10. For example, the power of 10 closest to 95,000,000,000,000 is 10 to the 11th. Notice that we have 3 6, 9, 10, 11 places. And then 100, 0, 0, 0, 0, 0, 0, 0, 0, 0, is our 10 to the 11th. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros. Okay? So the order of magnitude of 95, what is that? Thousands, millions, billion, 95 billion is 10 to the 11th. All right. Let's move down here and work a couple of examples. So I have a problem. T to the 5th, U to the 4th, over T squared, and U. Okay, the long way to look at this is this. This is T times T times T times T times T times U times U times U times U over T times T times U. All right? So these guys would cancel, and these guys would cancel, and these guys would cancel. And I would end up with 3 T's and 3 U's left. So it would be like T to the 3rd and U to the 3rd. Nothing is left on the bottom other than a 1, so we don't have to write that. Okay, let's do it with just the rules. When we divide with exponents, we use subtraction. So this is going to be T to the 5 minus 2, top minus bottom, and then U to the 4 minus 1, top minus bottom. So we just do that math. 5 minus 2 is 3, and 4 minus 1 is 3, and that would be my final answer. Number 2, A to the 6th, B to the 4th, C to the 10th, over A to the 3rd, B squared, and C. Rather than writing out this very long problem, I am going to just do the math. This equals A to the 6 minus 3, B to the 4 minus 2, and C to the 10 minus 1. Simplify that up a little bit. I have A to the 3rd, B squared, and C to the 9th. All right. Let's move down to some of the ones that might give us some trouble. Let's look at number 11. We have, in parentheses, 2C to the 3rd, D to the 5th, over 5G squared, all to the 5th power. And I've got to deal with that all to the 5th power deal. So I have 2 to the 5th power, C to the 3rd power to the 5th power, D to the 5th power to the 5th power, over 5 to the 5th power, and G squared to the 5th power. All right, now we have lots of powers on powers. We use multiplication to take care of that. We can take care of our numbers if we wanted to. 2 times 2 times 2 times 2 times 2, 1, 2, 3, 4, 5 is 4, 8, 16, 32. So 2 to the 5th is 32. 5 to the 5th is equally cumbersome. You might want a calculator at this point. 5 to 5 times 5 times 5 times 5 is 25. Okay, I do want a calculator at this point. If you're looking at your calculator, depending on what you're using, you want to look for the thing that looks like a little pointy caret symbol. It is your exponent. So you're going to type, it looks like this here. I don't have to just describe it. It looks like this. So you're going to type in 5, little caret symbol, 5, enter, to get 3, 1, 2, 5. We don't have to worry about those numbers needing to cancel with each other because there were only 2's up here and only 5's down here, and none of those cancel. C to the 3rd to the 5th is C to the 15th because I'm going to multiply. D to the 5th to the 5th is 25. And G squared to the 5th is 2 times 5 is 10. All right, there's no variables that match up top to bottom, so I believe we have found our answer right there. It's kind of a mess. All right, that was number 11, so let's also do something like number maybe 17. Try to just pick ones that look a little bit scary. 2a squared, b to the negative 7, c to the 10th over 6a to the negative 3, b squared, c to the negative 3. All right, I have some unhappy exponents. Look, he's unhappy, and he's unhappy. So let's make everybody happy. The 2 is happy, so let's leave it. The a squared is happy, so let's leave it. The c to the 10th is happy, so let's leave it. Okay? The 6 is happy, so let's leave it. The b squared is happy, so let's leave it. Okay, let's deal with unhappy. B to the negative 7 is unhappy. B to the 7th. So notice, as soon as I put this guy in the bottom, the negative is gone because it's happy. Okay? Let's deal with a to the negative 3. Is a to the 3rd. As soon as I put it up there, it's happy. So I take away the negative. Okay? C to the negative 3 goes up here, and now it's happy. Okay? As soon as I put it where it wants to go, and it just wants to go where it isn't, right? Then it's happy. All right. This is a mess. We need to combine like things. Let's look at that 2 and that 6. Okay? There's a common 2, right? 2 goes into 2 one time, and 2 goes into 6 3 times. So we can have a 1 and a 3. All right. I happen to have lots of a's going on here. If I have a squared times a to the 3rd, that means I have 5 of those a's. So I'm just going to put a to the 5th. I add them. When a squared times a to the 3rd, I add the exponents 2 plus 3. I also have c to the 10th and c to the 3rd. So I'm going to have c to the 13th, 10 plus 3. Okay, on the bottom, I have b squared and b to the 7th. So I'm going to add those guys together and get b to the 2 plus 7 is 9. All right, we're just pretty close to just being able to write this. I can write that 1 if I want to, or I can just put a to the 5th, c to the 13th over 3b to the 9th. Is this a monomial? Yes. Ooh, has a variable in the bottom. But it doesn't have a negative exponent. It does have a variable in the bottom. So it's not a traditional monomial, no. But it is a simplified expression. All right, I'm going to stop there, send you to work on your Alex problems, and let's just sum up what we talked about today. Okay, monomials may also be divided. To divide two powers that have the same base, we subtract the exponents. To find the power of a quotient, find the power of the numerator and the power of the denominator. That anything on the outside of the exponents is going to go to each part inside I'm not sure I said that right. Anything on the outside of the parentheses is going to affect every piece inside the parentheses. Okay, any non-zero number raised to the power of 0 equals 1. It doesn't matter what it is. It can be x to the 0 or 50 to the 0. It's going to equal 1. Okay, expressions can also have negative exponents. A non-zero number raised to a negative integer power is the reciprocal of the same number with the opposite or positive power. Simple way of saying that is a negative exponent is unhappy and it wants to go where it isn't. So if it's in the top, it wants to go to the bottom. If it's in the bottom, it wants to go to the top. Then it becomes happy and positive. Okay, a fraction that has a negative exponent can be rewritten as a reciprocal. What if I had this? 2/3 to the negative 1. What do you think that's the same as? Well, we apply the exponent to each thing, which means it's very unhappy. To make it happy, we get to move everybody up. So that's what that means. It just becomes the reciprocal. Remember that negative exponents are not negative numbers. They are just negative exponents that tell us to flip things over. The order of magnitude of a quantity is the number rounded to the nearest power of 10. We also saw that little piece, which just happened to get kind of tucked in here. So let me know what you still have problems with, and we'll talk.